Thanks very much for the invitation to speak, Joe. It's an honor to be here, and I apologize for polluting the seminar with English, but it is what it is. So the Poisson summation conjecture that I'm mentioning here is the conjecture that Joe has mentioned earlier that was introduced by Bergman and Kazhdan in the case of a monoid, and then expounded upon by Cho and by Laurent Laforgue, and then also extended in certain cases to spherical varieties by Saklarides. And I want to concentrate on one particular case that has some interesting consequences, and I'll actually start with the prospects. And before I forget, this work is joint with Gu, my students Pam Gu, Chunchen Su, and my postdoc Spencer Leslie, who's, I guess, not my postdoc anymore. He's going to Boston College. So here's the prospect that I'm interested in. So this is prospects. So let F be a number field. And I'll give myself a triple of integers R1, R2, R3. And I'll just let this triple be R underline. And I'll look at the product of the three general linear groups. And by the tensor product, triple tensor product, I mean the Langlands L function attached to the tensor product representation. Okay, so if I have pi equals pi 1, tensor pi 2, tensor pi 3, cuspidal automorphic representation of GL RAF, I can form the corresponding Langlands L function, which you might also write LS pi 1, pi 2, pi 3. All right. So why is this an important case of the general theory to study? If we knew the analytic continuation of these things, so if we knew that these things were nice, and we add together the converse theorem, plus a little bit more, the converse theorem in its current form is not quite enough, then we'd obtain the Langlands transfer that's attached to the tensor product representation GLR1 on the other hand, if I give you a reductive group or a group in any reasonable setting and a faithful representation, then any other representation can be obtained by taking sub-representations of tensor products of that representation and its dual. So this is a basic case to study. Okay. So when is this known? It's actually a bit depressing. So here's the graph of where this is known. So if R1, I can renormalize, so R1 is arbitrary. So if R3 is equal to 1, then this is Jacquet, Piaczewski, Shapiro, and Shalaika. This is Rankin-Selberg theory. If this is 2 and 2, this is due to Ramakrishnan, because he established the automorphy of the tensor product of two GL2 automorphic representations. And then for 3 and 2, this is Kim Shahidi. And again, they established the automorphy of the tensor product of a representation of GL3 and GL2, and so then you can apply Rankin-Silberg theory. Okay, and that's it. That's all we know. So what I want to describe is a pre-integral representation. Maybe I'll say something more about what I mean by this for LS pi tensor. What is needed to deduce analytic continuation and some local questions that should elaborate the situation. Okay. So it's actually really nice that Cho talked about Braverman-Kazhdan spaces this morning, because that's what I'd like to talk about now. I will try to keep the notation consistent, but I have to, somehow my brain won't work correctly unless I take the unipotent on the other side. But other than that, I'll try to be consistent. So this is section 1, and this is Poisson summation for Braverman-Kazhdan spaces. All right, and this is in the title known cases of this Poisson summation. All right, so I'm going to work, actually I'm just going to work in sort of the opposite extreme of what Joe worked on. So he worked with a maximal unipotent subgroup. I'm going to work with a maximal parabolic instead. So let's let P be a maximal parabolic. In a simply connected split G. All right, so I'll let XP be the corresponding quotient that we saw earlier, although I'm putting the parabolic on the left there. I'm going to refer to this as a Braverman-Kazhdan space. You could also refer to it as a pre-flag variety. Okay. And so then, in the case at hand, as Cho explained, the closure of this is a quasi-affine space. The affine closure is just a point union this space, because we're working with a maximal parabolic. Okay, so by work of Braverman and Kazhdan, we have a short space S XP AF. And this is contained inside the space of smooth functions on the smooth locus. And it intersected with the L2 space of XP AF. So the convention here is that functions on the short space, which is some singular space, don't have to be defined at the singular locus. So, which in this case is just a point. All right. And I should mention that it's quite difficult in practice to work with the definition that we saw earlier of the, so Braverman-Kazhdan, as Cho said, defined this Braverman-Kazhdan, this short space to be compactly supported smooth functions plus their Fourier transforms inside L2. And if you want to work analytically, it's a very difficult definition to work with. So in order to get something that you could work with analytically and estimate and so on, it took a little bit of extra work. And so I did some of that with Liu, and some of that with Sue and Leslie. So you can actually give a definition in terms of growth conditions on the Mellon transforms that Cho mentioned, and it works uniformly in the Archimedean and the non-Archimedean setting. And so that's that. But anyway, you can give this definition. And we also have an explicit Fourier transform, FP from the Schwartz space to the Schwartz space of the opposite parabolic. Okay. All right. So when P is self-associate, you can renormalize this to get a Fourier transform FP from the Schwartz space to itself. And these are extend to L2 and they're unitary, right? And then finally, using the theory of Eisenstein series, one has a Poisson summation formula. So for F in the Schwartz space, I think I'm missing my notation here. I'm not. AF, we have that the sum over X in XP of F is equal to the sum over F P P op F of X, X in X P op of F. For F satisfying local conditions. And more explicitly, what you have to assume is that F factors, F is, say, a pure tensor, and at one place, the function is supported in the open locus, and, sorry, the smooth locus, and its Fourier transform is supported in the smooth locus, so pretty natural things. You can get rid of that assumption if you're willing to put in some residues of Eisenstein series into the expression. The only case I know where you can give sort of a fully satisfactory expression is in the case of where you're working with the zero locus of a quadratic form. So I worked that out recently. And what's interesting in that case is you get a sum over all the forms in the same width class. Okay. All right. So how are we going to apply this? And sort of as a bit of a warm-up, okay, I'm going to have R be in F algebra. Yes. Nothing in zero. So the value at zero is not defined, right? So so F satisfies, you can either do one of two things. You can say F satisfying local conditions, which kills that. Yeah. Or you can incorporate it, and so you get residues of Eisenstein series, but it's important to note that it really does have a pole at zero. I mean, you have to regularize. And again, the only case I know where I have a completely geometric interpretation of the side terms is the case of the zero locus of a quadratic form.
But you need the local condition for F and the Fourier transform.
Yeah.
Which is not obvious.
Right, so I mean, okay, so you say F is equal to F V1, F V2, F V1, V2, and you want F V1 to be compactly supported, and then you want F X or PP op of F V2 to be in the smooth locus, right? That sort of thing. Yeah. Okay. All right, so I want to look at the group HR, which is H1, H2, H3 in GL2 cubed of R, where the determinants are equal. Okay, let G be SP6, P inside SP6, the Siegel parabolic. So this is the parabolic that stabilizes some maximal isotrophic subspace. And then there's a natural map. H goes to GM semi-direct product with SP6, GM cross XP. And if I take pi, a cuspidal automorphic representation of HAF, phi in its space, and integrate along the Poisson summation formula, I get the analytic continuation of LS pi tensor cubed in this case. All right, so meaning this is the 2, 2, 2 case. And this is essentially this is the integral representation for the triple product L function given by Garrett, Piatowski, Shapiro, and Rallis. So, okay. And so you might ask, how do you generalize this? There's some problems because if you do the sort of stupid things like try to take a larger number of GL2s and embed it in some bigger symplectic space, none of these things seem to work. Okay.
What do you mean by integrate along Poisson summation?
So I take, this thing has an action of R of G, so let me see. Let me write it down. This is the whole paradigm that you take RG F, so you have some sum over some space. And this is sum over X in XF of Fourier transform on X, RG F of X. I take so this Fourier transform will not commute with the action of G, whatever it is, right? It will usually commute up to some anti-automorphism, or maybe it'll change this to G inverse transpose or something of this nature. So I take an identity of this type, I multiply both sides by phi of G, and then I integrate over G, or this is the usual thing, G is GF on GAF, right? Okay, and this gives, it's just like in Tate's thesis, this gives you the functional equation. Okay. So that's what I mean by integrate against phi. Okay. All right, so I want to now explain how to generalize this setup. And essentially, we're going to be using the same embedding, but kind of giving a unipotent thickening of it. So that's the next bit. So maybe I'll start on this. Okay. Okay. So. All right. So.
The left-hand side is the integral representation of the triple product, and you use the right-hand side to get the
Yeah, that's exactly right. Yeah. And the thing that may be funny is that when you pull this out, you get some sort of, in this case, the inverse transpose, I mean, because we're just working with GL2, I mean, it's just dividing by the determinant. That's the analog of the inverse transpose, but yes, that's exactly right. And really, I should put something like a det G to the S dg, and then a det G. And when you do that change of variables, this is going to flip. Okay. And you're going to get some normalization factor. So I'll just remind you that I'm using this notation and r minus 2. Okay. I'm going to write G of R is set of G, V, H, 0. So G, H is in GL, R minus 2 plus H of R. And V is in M, R minus 2, 2R. So I mean, by this I mean, let me write it down this time. I have to sort of keep track of 3 terms at once. Okay. And Ni okay. I have this unipotent group. I have MR G delta lambda 1, where G lambda is in GL R minus 2 R plus R. And I'll let N be product from I equal 1 to 3 of Ni. Okay. So those are the groups I'm going to use. And what's the space? So the space, I apologize for this. It's easier in LaTeX to determine the difference between a calligraphic M and a straight script M, but this is the space I'm going to be looking at. And M. Okay. And so what's the action then? So I have an action M, N cross G to G. And this is just given by left and right multiplication. Right? And what I want to do is I want to use this to induce an action on M cross a particular short space. But let me, or sorry, a particular Berman-Kajdan space, but let me get there. So let's let N naught of R be 1T1, 1T2, 1 minus T1 minus T2, 1. I'm viewing this as a subgroup of SL2 cubed. So N naught actually lives inside the group H that is still on the board here. Okay. All right. And the observation is that this action that I've defined descends. So it descends to define an action R from Mn cross M cross N naught H cross G to M cross N naught H. Right? And how do I see this? I mean, the point is that what is G? Not as a group, but as a set, G is M cross H. So this action of Mn on the left and G on the right gives me an action on G. Tautologically, it gives me an action on M cross H. And I've set it up so that it actually descends to an action here. Okay. It's the way that I've chosen this subgroup N. Right. So if I choose a suitable base point for a suitable base point gamma 0 in xp, which is this symplectic quotient that I mentioned earlier. Okay, and I guess I should take F points. N naught is the stabilizer of gamma naught in SL2 cubed. Okay. So what does that mean? It means that I can take this action and I can extend it to the Braverman-Kazhdan space that forms some sort of compactification of this. Okay. So let me write y equals gm cross xp. Maybe I'll put an xp bar where I'm looking at this Braverman-Kazhdan space again. And then I've constructed an action R from Mn cross M cross Y cross G to M cross Y. Okay. And let's see, while these things are still on the board, this is just GL R minus 2. In each factor, it's GL R minus 2 across some matrix. This is this thing that is written right here. Okay. All right. Okay, so here's a proposition. So one thing that's sort of funny about this is that neither this nor this are reductive groups, right? But you can still sort of say what you would mean by a spherical variety under a non-reductive group. I mean, you still have a notion of a Borel subgroup, and you can say there's an open Borel orbit. So just a nice thing to check is that M cross Y is normal and admits an open orbit under Mn cross G. Okay. So if you'd like it spherical under the action, right? If you want to extend the definition. Okay, so then what's the integral representation? And I'm just going to take this object and integrate against it. So okay, so So pi equals pi 1 tensor pi 2 tensor pi 3 is now an automorphic representation of GLR AF. R is arbitrary now, and I'll say cuspidal. And pi prime is pi 1 tensor pi 2 tensor pi 3 prime. This is a cuspidal automorphic representation of this. Okay. I'm not going to assume that they're unitary. Just so I don't have to put more parameters in things. I mean, just as a remark, I can always factor pi equals pi 1u dat s tensor pi u 2 dat s1 dat s2 pi 3 dat s3, where the pi u's are trivial on the usual copy of the positive real numbers and the embedded diagonally in infinite places of GL and R. And so I can think about these things as, I can talk about a function of pi being holomorphic, et cetera, by saying that it's holomorphic as a function of S1, S2, and S3. Okay? I can also talk about things like the real part of pi, which I think of as being an element of R cubed. Okay? All right. So let me recall that, or maybe state, depending on what you've read, I guess, that the short space of a smooth affine space is defined. So if you're working in a non-Archimedean setting, it's compactly supported smooth functions. If you're working in an Archimedean setting, you can work with the definition that was set down by Eisenbud and Goresky. Or if you, I mean, you can just think about compactly supported smooth functions if you want. So I can define y this short space to be a complete at the infinite places. And I just tensor with what's happening at the finite places. Okay. And here's the integral representation. So it may look a little bit intricate, but I can't speak this morning. But essentially what I'm going to do is I'm going to take a test function f that's in this short space and just integrate against what I've shown you already. I've constructed a group action and whatnot. Okay, so what is this? So I take the mn cross g. Maybe I'll call this h to make it, no, I'm going to write it down wrong. Better than just Okay. And here, rather than writing down all of the variables here, I'm just using d omega to denote the measure induced by a left Haar measure, say on G across Mn. Okay. All right. And here O contained inside M cross Y is the open orbit. Okay. And the first, so this converges in a suitable cone, maybe for real part of pi, real part of pi prime, and real part of S in a suitable cone. In R to the 7th. Okay? All right. So let me now just talk about how this unfolds. So what's the meaning of this thing? Okay, so let me let U underline R inside GL underline R be the usual unipotent, well, the unipotent radical of the Borel of upper triangular matrices. Okay. Give myself a generic character. So I'm going to expand this in terms of Whittaker functions. So I give myself a generic character. And invariant on the left underneath URF. And then I'll use W phi psi to be the usual Whittaker function. All right, this is the global Whittaker function. I'll pick a suitable base point in MF cross YF. And then, oops. What's the local expression for this? So the theorem is that this gadget unfolds. I'll write down the local expression. Okay. So again, for parameters in a suitable cone, this thing unfolds to an integral of W psi phi G2 G1 W psi phi prime of G2 and then something that involves the Whittaker function, or sorry, the Schwartz function. And then dz, dg, dh, d times lambda. Okay, so what are these integrals over? This integral is over G2 in UR minus 2 of AF, GLR minus 2 of AF. And this integral is over lambda z g1 and h in AF times cross AF I think I need an H here. Okay. All right.
Jayce,
Yes?
can you just address what this should generalize? This should encapsulate at the same time Rankin-Selberg, and it should also encapsulate Garrett.
Yes.
For Garrett, you would take R to be 2, 2, 2.
Yes.
And then R minus 2 would render phi prime to be trivial.
Yes, exactly.
And then for Rankin-Selberg,
Rankin-Selberg is the inner integral. It's the integral over G2. So the integral over G2, if you ignore this G1 stuff, right? The integral over G2 is the integral representation for pi times pi prime.
I'm sorry, so Rankin-Selberg had 2 cuspidal automorphic forms, but you wrote on the board like 6 cuspidal automorphic forms.
Right. You're right.
So
Thank you. That's the product. Right. So, okay. I mean, one thing, okay. Certainly, I would be much happier if I had some idea how to prove Poisson summation for the monoid that's attached to the triple product representation. But the goal here was to start with something that I knew how to prove a Poisson summation formula for, and try to build something that would give something that we don't know already. I'm not claiming that. I'll tell you what the obstacle is. I mean, otherwise I would have led with something more exciting. I mean, but I mean, this is okay. Okay, so all right. So let me say, so one thing that's problematic is that it doesn't look like this is the correct L function in the sense that, so I guess I'll write down, this is an approximation of the L function that we want. So somehow the short space is not quite correct. It needs to be modified. So sort of to first order, it's correct. And let me make a statement that's precise along those lines. So here's the theorem. So for suitable choices, phi prime f, you have that z phi prime f s divided by L of s plus 13 plus some ri. And I'll define these terms in a moment. Oh, this is a prime. So this is holomorphic in a suitable cone. And if pi and pi prime are essentially tempered, the cone intersects the critical strip. Non-trivially. So I think we should be able to do a little bit better than this. But so remember, oh, I forgot to say that omega is the central character of pi, and omega prime is the central character of pi prime. So we have several parameters running around, so you have to be careful about where you're taking them. But the important parameter here is the S, and the important L factor here is this one. So my expectation is that if we had the correct Schwartz space, then the L function that we'd be getting is exactly this denominator. Okay. All right, so we're seeing this. This is known stuff. This is just the Rankin-Selbert product, but this is the thing that we want to isolate. Okay. Okay. So let's see, I've got about 15 minutes left. So here's a philosophical comment that I think is helpful. So Eisenstein series are not enough. So what do I mean by this? So how did we construct this integral representation? We had an action of a unipotent group N on this space M cross Y, right? So this is the same sort of space that's appearing in Garrett's integral representation, right? So in Garrett's integral representation, you take the projectivization of this. The Eisenstein series naturally lives on the projectivization of this space, okay? So you could say, okay, well, why don't I forget about the Schwartz space and just work with the Eisenstein series? You can't do that because this action does not descend to an action on the projective space. Right? I mean, it takes a vector here and it takes an element here and constructs a vector that you add here, right? The point is you can't add a vector in a line. You can only add a vector in a vector. Okay? So it's just so somehow the Schwartz space and not just, I mean, it's not artificial to work with the Schwartz space, even though the analytic properties of that Schwartz space are completely controlled by the Eisenstein series. All right. So here's the applications prospects. So I guess I already talked about prospects, but so let's recall that M is just GL R minus 2 cross M R minus 2, 2, okay? And this is just a vector space, right? So we have a Fourier transform on this. So we have a Fourier transform F R minus 2, 2 from M R minus 2 to AF to itself. I mean, just pick a pairing on it. We have a then we have a Fourier transform F, which is given by the identity on S GLR minus 2, AF, tensor this F R minus 2, 2, tensor the identity on S AF times, tensor the Fourier transform on Y, or on X. And this thing, maybe I'll just continue this. So this thing goes from the short space of MAF cross YAF to itself. Okay? And we have a Poisson summation formula for this. Summation formula. Okay. All right, so what would you want to do? You want to take this and you want to integrate it against the actions of the group. So what's the problem? The problem, okay, so first, G and M action, okay, maybe I'll say it this way. The relationship between the G and M action and F is understood. But the N action, NAF, and F, well, don't play well together. So I don't actually know, other than a tautological statement, what a good, so we certainly have, we can act by the inverse of this, act by this, and act by this again, get some action. But I still don't know a good interpretation of that action. And sort of this is the key to figure out, you know, what, probably in order to come to grips with that, one has to modify the short space and perhaps modify the Fourier transform in some setting. But, you know, fortunately, there's some local questions that we can ask that should lead to this, and at the same time give us some information about the local functional equation. So I'll end with that. This is an hour and not 50 minutes, right? Is that the standard is an hour, right? Yeah. Okay, all right. Okay, so I'll finish up with that. Okay, so now this is the global theory that we've talked about. So what are the local avenues? All right. So we'll work in the non-Archimedean setting. And we want to study R tilde, which is the map from S, it's a map from N, F cross S, M, okay, all right, and the Fourier transform sort of tautologically gives us an isomorphism between the coinvariance under NF and the coinvariance under this twisted action. Oh, I need to be doing my script FM thing everywhere. Okay. And there's a map from this to the space of smooth functions on NF, MF cross YF. at least if we throw out some, I mean, maybe I'll put a prime here. We want to throw out, just look at the locus on which NF acts freely. Right? So then the question is, to construct some space Z with an action of G cross M and an equivariant map such as this, okay? And this space C should give us whatever is on the other side of our global Poisson summation formula. Okay? Unfortunately, I mean, how would one go as, okay, let me make 2 remarks. I mean, first, there's a natural way to try to construct this, right? How do you construct a co-invariant on a space? Well, you integrate, right? You take a function in here and you integrate over NF. Of course, it doesn't converge, right? So then you regularize it. But this is something that you can do because we have an explicit formula for this Fourier transform. So in a recent paper with, so the Fourier transform already in the Braverman-Kazhdan space is fairly explicit. But in a recent paper with Sue and Leslie, we created a completely explicit expression for fx that just looks like a Fourier transform. You essentially embed it into the, via the Plucher embedding, you choose a form, integrate, and then you normalize by some abelian L factor. It's very easy. So the question then is to understand, I mean, to use that description to construct this space ZF. Okay? Right? So that's the first comment. That's the first thing that one should try to do. The second comment is that once this space should satisfy a multiplicity 1 result, because we already have this corresponding global multiplicity 1. That's it unfolds, right? So currently we're working on proving that local multiplicity 1 result. And so given a resolution of that, plus a construction of this space ZF, you get local functional equations, right? Because, I mean, what are you doing? You're constructing 2 different functionals. You have multiplicity 1 here, so you'll have multiplicity 1 here, and that'll give you some local functional equation. Okay? Whatever gamma factor appears in that local functional equation should inform the way in which, or the manner in which this global short space should be modified to sort of get the true short space. And let's see. And I think I'll stop there. So the general idea is to take yes, so I mean the general idea is if you have, let's say you have Poisson summation formula for x1 and x2, right? And you have some group action that mixes them, right? Then it's not obvious how to get a Poisson summation for, so if I take, say, let's say I have a unipotent group action, right? Then the question is, can I obtain a Poisson summation formula for the quotient and let me be, I mean, I guess, I mean, there's not, maybe, let me stick with unipotent for the moment, right? I mean, can I obtain a Poisson summation formula for a quotient? And it will not go back to the same space. So the example to keep in mind is if you have if you take a pair of vector spaces, V1 cross V2, and you take an additive group action, so you take like T, V1, V2, mapping to V1 plus T, V2, V2. Okay, then you can obtain, you just do the Poisson summation formula on the pair of vector spaces, right? And it will give you some other space, and it will not give you the same space. I think what it will give you, I think it'll give you something like the perp space to V2 and V1 or something like that. So you can see in examples, that you're not going to get the same space out on the other side. But the question is, the example gives you a situation in which if you solve this problem, there's dividends, right? So the general question, I think, would be this, right? And it's sort of nice because if you take this unipotent group action and you have a suitably, of course, one would like to be able to do this without explicitly computing anything, but in the situations where we have an explicit formula for the Fourier transforms here, you can hope to answer the corresponding local question by constructing coinvariants.